वहाँ से साउंड मिलेगा ना।
Good morning, ladies and gentlemen, and a very warm welcome to Day 2 of the first Geotech Asia International Conference 2025. We are about to start the sessions. We will start it off sharp at 9 a.m. It's truly wonderful to see all of you once again this morning. Faces that radiate with energy, passion and curiosity that made yesterday such an inspiring start to this 4-day journey of knowledge and collaboration. Yesterday, as we inaugurated this prestigious conference, we celebrated the coming together of geotechnical minds from across the continents. Researchers, academicians, professionals and students, all united by a shared vision to move forward together to shape the future of geotechnical engineering under the theme GeoVadis, the future of geotechnical engineering. The word GeoVadis, as many of you will recall, beautifully fuses geo with the Latin vadis, meaning to move forward. And truly what we witnessed yesterday was a living embodiment of that phrase, a collective movement toward thorough, insightful keynote lectures, thought-provoking discussions, and a spirit of camaraderie that transcended borders. As Dr. Arul Joseph, the president of Indian Geotechnical Society, beautifully remarked, the making of Geotech Asia 2025 is not just a story of a conference, it's a journey of vision, resilience and friendship. And as Dr. Mark Belaus, the president of ISSMG, so aptly expressed, this gathering represents geotechnical brothers without borders. Yesterday we witnessed this sentiment come alive in every handshake, in every session, every discussion and every moment of shared learning and shared smiles. We saw the geotechnical community not as a collection of individuals, but as a global family bound by shared purpose and professional kinship. The Indian Geotechnical Society, with its rich legacy and vibrant community, stands at the forefront of advancing geotechnical knowledge in India and beyond. It was IGS that had the honor of hosting the very first Asian Regional Conference on Soil Mechanics and Foundation Engineering back in 1960 in New Delhi. And now, more than 6 decades later, IGS once again creates history by hosting the first ever Geotech Asia International Conference, a proud and defining moment for our geotechnical fraternity. Our heartfelt appreciation goes to IIT Mumbai, the collaborated institution, and the IGS Mumbai chapter, the joint facilitator, ably supported by the IGS Kochi chapter for bringing this vision to life. We also extend our gratitude to all our sponsors, partners, and supporting organizations whose contribution have made this event possible. And above all, we thank each one of you, our delegates, participants, and speakers for your presence, your ideas, and your energy. You are the heartbeat of this conference. Today, as we step into Day 2, we continue this enriching journey. The day ahead promises to be equally engaging and intellectually stimulating, featuring 3 invited lectures, 4 keynote lectures, panel discussion, and 6 parallel technical sessions spread across diverse themes. Each of these sessions represents not just a presentation of work, but a story of research, innovation, perseverance, and collaboration. It is in these interactions that we discover new possibilities, question existing paradigms, and inspire one another to push the boundaries of what's possible in the geotechnical field. Day 2 also provides us an opportunity to pause and reflect, to think about how ideas we exchange here can translate into meaningful action, how our discussions can influence practice, policy, and education, and how the bridges we build here session. Welcome you sirs onto the stage.
और ये भी लेना था तो हेलो ये भी लेना था वायरलेस के लिए बड़ा वाला है नहीं उधर ले ले
Request the chair and co-chair to take over the session.
Very good morning to all of you. Welcome to the session third today. And for the last 2 days, we have very intensive technical presentations. Apart from
Thank you for giving an opportunity.
I hope that
It was a great opportunity. No, yes, sir. I asked you, sir. I
I
don't want to miss this kind of technical thing.
more technical activities.
Never go out.
And today,
Sir, I
in
apologize
this
if
session,
you get hurt by my any small
we
words.
have
The day I told you, no, just, sir, I can go to silver. Don't take it seriously, sir.
and then another presentation is also there. So we come back to the details of those the presentations, etc. And I would say let me thank the organizers for giving us this opportunity to chain this particular session. So the first is we will call upon the first is the speaker. Okay, the first one is Walter. Professor Walter, sir, please come on to the stage to give the presentation.
Ladies and gentlemen, at the plenary session 3 today, we have 3 invited lectures and 1 keynote lecture. Invited lecture 1 is by Professor Kesufi Daniel Antonio from SESI-SPA on the topic use of geomembranes in embankment dams and their long-term behavior and service. Welcome you, sir.
I'll give you Professor Daniel Antonio, so that to give you the invited lecture. Thank you.
Thank you very much for your kind invitation. Thank you to our chairs, to the current President of IGS India, the Geotechnical Society, all the friends of India. Today my speech is related to the use of geomembranes and embankment dams, and particularly on their long-term behavior and service. I acknowledge my author, Professor Domenico Trofeo of the University of Pavia. The concept of applying geomembranes is relatively simple. To apply a relatively low material to minimize or to completely stop the passage of water through an embankment dam. So this is the core of my presentation. But I am confident that in the near future, this concept to apply geomembranes could be also extended to tailing dams in order to avoid very important environmental disaster, as it happened last February this year in a tailing dam in Zambia, in Africa, where an important pollution has been experienced in the Kafue River following a complete collapse of that tailing dam. Therefore, in this next 20 minutes presentation, I am trying to summarize my more than 40 years experience on the use of geomembranes in dams. So I start with some introduction. I'm speaking both on application of new construction of dams and also use of geomembranes for rehabilitation of different types of dams. And I conclude with some elements of long-term behavior of geomembranes. As you may know, the first application to a dam was experienced in Italy in 1959 on a rockfill dam 32 meters high, where an elastomeric geomembrane, a polysulfide 2 millimeters thick, was applied and protected by cement concrete slabs. This was a very historic application on a quite important slope, 1:1, and after this very historic application, a lot of more than 300 dams presently in the world are waterproofed with geomembranes. Most of them, almost 70%, are embankment dams, the subject of my today's presentation, about 20% on concrete and masonry dams, and 30% are rolled compacted concrete dams. These are the statistics from ICOL, the International Commission on Large Dams. So I do not spend time on the history of this application. After this very historic application in southern Italy in 1959, a lot of other application was experienced, like in the United States in 1960, the famous Terzaghi Dam. So, dealing with embankment dams and also reservoirs, I am today, my speech will be only on the upstream slope application, while there are about 10% of application of geomembranes in dams that are not on the upstream face, but are in the central position in the embankment dams, like in the geotechnical engineering, they zoned embankment dams with a central clay core. This is the same concept, but today I have no time to present this interesting new application on the central location. So, the statistics from ICOL that is not really updated, is dates back to about 15 years ago, and the most of applications are now on PVC, polyvinyl chloride geomembrane, that is almost 50%. I will illustrate you in the next slide. For the new construction, there are two main applications where the geomembrane is left exposed to atmospheric agent, and another type of application in which geomembrane is covered or protected from other materials, like in the first case in southern Italy, which was protected by concrete slabs. So of course, exposed geomembranes for the time being account for approximately 30% of geomembrane used on the upstream slope of embankment dams. And of course, the first application dates back in the 80s, more than 40 years ago, and they were more on buffer dams, so on a provisional application of dams. This, for instance, is a Bilancino Dam to protect the city of Florence from flood, in which you could see an embankment dam with the central core and a coffer dam that was protected by a PVC geomembrane. The same applied to other dams in southern Italy. For instance, this is the case of the Locone Dam, in which the coffer dam was protected by an exposed rubber geomembrane. Here you can see some aerial view dates back more than 40 years ago of this important historic application for exposed geomembrane. Also, the cover of water-proven dam construction in 87 was explicitly illustrated this application of the Lobone offered. More recently, there are a lot of important applications of exposed geomembrane bank and dams. Here is Cerro Lindo Dam in Peru, less than 20 years ago, with the bituminous geomembrane almost 5 millimeters thick. The dam age of about 30 meters was applied on a slope, 2 horizontal, 1 vertical. Also in this continent, in Laos, less than 10 years ago, a PVC composite geomembrane, 3.5 millimeters thick, was applied in this important dam, 8-meter elevation. See, here some PVC spray to apply and to weld the composite geomembrane sheets on the upstream slope that then in Laos. Of course, it's very important the welding of the contiguous sheets of geomembrane to ensure complete waterproofing of the system. This is a completion of stage 1 in this dam, Laos, and this is a completion of overall dam. Exposed geomembrane, so exposed to atmospheric agents and all the various attacks. This is a case of a reservoir in the United States, in Maryland, in which a bituminous geomembrane more than 5 millimeters thick was applied for drinking water reservoir. And these are the phases of application during the application of the geomembrane itself, and on the right during the service, even in winter time with this exposed geomembrane. Okay, we have seen some example, also recent example of exposed geomembranes, that is covering 30% of applications, 70% of applications are protected, covered geomembrane. So the concept is very simple, to apply a concrete elements on the top of geomembrane or soil ballast to protect the geomembrane itself on the upstream. This is an historic application in France that dates back almost 50 years ago, 26-meter L'Hospedale Dam in Corse, where the bituminous geomembranes 4 millimeter thick was applied. A more recent application in the island of Cyprus, this in dam experienced the application of a high-density polyethylene geomembrane, 3 millimeter thick, that was covered by interlocking concrete blocks. The dam is 37 high. This quite important application dates back to almost 40 years ago in Albania, is Movilla Dam, age more than 90 meters, in which a geomembrane was protected by not reinforced concrete slabs. You could see here, it resulted in one of the first important applications of this concept of composite geomembrane, that is formed in factory, so it's manufactured in a certain way, with a PVC geomembrane 3 millimeter thick, associated in factory with a geotextile about 700 grams per square meter. So the geotextile has a function to protect the geomembrane on the application on the support that you could see here, and in that case the geotextile could not require an heavy surface preparation of the support. This is the application of unreinforced concrete slabs, and over the composite geomembranes in Albania, an extra layer of polypropylene geotextile, about 800 grams per square meter, was applied. You could see the casting of non-reinforced concrete slab by an alternate method. And it's important to note that this system allows a very fast application of about 1 month for a dam of more than 9-meter elevation. More recently, 25 years ago, in France, this application Lagalot Dam, 42-meter application, absence slope of 1 vertical to horizontal, of a bituminous geomembrane, 4 millimeter thick, that was protected by concrete about 100 millimeter thick, reinforced with polypropylene fibers. This very quickly some details of the application of this bituminous geomembrane in France. Of course, it is important to apply some system to control the seams, the welding in between the different contiguous sheets of geomembrane. Of course, also in the case, polypropylene geotextile was installed for a geomembrane protection before the application of 100 millimeter thick polypropylene fiber reinforced concrete over the bituminous geomembrane. This is a photograph of the dam that I took 3 years ago, 22 years after the application. Okay, these were the application of concrete element to protect geomembranes, some application of soil layer to protect geomembrane. A very important historic application is being realized by the United States Bureau of Reclamation in the early 80s for this pumping storage reservoir in Colorado, Mount Elbert, in which for the first time in the United States a geomembrane was applied, only 0.5 millimeter thick and protected by a wrap with gravel. But this marks an important application because after this reservoir, the installation of the geomembrane marked a turning point also in the United States. More recent application of more complex system in this reservoir in France with the double geomembrane system. I do not spend time to explicitate all the various layers of geosynthetics used in this application in France, just to see the final placement of the gravel cover layer over the entire geosynthetic system. I have to say today I have no time to spend my presentation, but yesterday there was an interesting debate organized by the Federation of International Geoengineering Society, FedEx, on the concept of use of technical engineering for the climate change. And in the Alps and also in other countries, not only in Europe, we have experienced in the last years a lot of geosynthetic application to protect the reservoirs for allocating water for the snow application on the Alps. Finally, concerning the application of geomembranes, not only in new construction but also in rehabilitation of them, just 3 examples. This is the application of an exposed geomembrane that next about 20 years ago on a cement concrete face rockfill dam, particularly in this dam in Norway, dam, in which there were important leakage in the concrete face. A composite geomembrane 2.5 millimeter thick was installed in 1 month and a half instead of 2 full summer seasons that were required by the second best rehabilitation option that was foreign materials. And you could see here some particularly attractive photos of the exposed German plains in presence of snow and ice during the winter season. But the most important was this type of application of German plains involved a decrease of the leakage from 440 liters per second to about 2 liters per second after this application.
Professor Kajabi, 2 minutes, please.
Okay, thank you. The same concept is applied, could be applied to concrete-based bituminous dam, and also to stone masonry dam. I'd like to show you a very important application in your country, in Kadambarai in India. It was a masonry dam in which a system involving non-mojo textile and the composite German plain, allowing 20 years ago to after the repair, to reduce the leakage from about 40,000 liters per minute to 30 liters per minute. So finally, some consideration on long-term behavior of German plains, and these were the Contrada Savetta Rockfield Dam, the removal of concrete protective slabs that was done in 98 after almost 40 years of application, and we discovered no variation of the mechanical and hydraulic characteristics of these German plains after almost 40 years of application. A more important research has been done recently by our laboratory on dams located in Italy and France on the Alps between 1,000 meter elevation and 2,500 meter elevation, and these are the dams in which these dams are in fact concrete and masonry dams in which the German plain is completely exposed to atmospheric agent. You could find the result of this experiment in the written contribution. And of course, our policy is to monitor the dam by visual inspection, but also to take sampling from the dams in order to ascertain their properties during the time through a number of tests. And the most significant test for this type of dams is the variation of plasticizer content in these dams that could allow to us, through some model, to detect the life, the residual life of these German plain dams. For instance, this dam will be 42 years. In these other dams, Composeco dams, masonry dams, will be almost 50 years since application. So some conclusion, we have seen that most of application of German plains are in embankment dams. The durability is a major consideration of the dams, particularly if the German plains are exposed. Durability is of course an issue for all material used in the dams, and not only for geosynthetics. In dams, unprotected geosynthetics are exposed to harsh conditions, and to ensure durability, particularly in exposed condition, the geosynthetics must be carefully selected, should be regularly monitored, visually inspected, and to check durability, my suggestion is that the geosynthetic could be also tested periodically. Another way to look at durability is the number of years of successful experience in large dams with the various types of German plains. For instance, the first one in America now is 66 years of application. The quality of the polymer used for manufacturing related to geosynthetics, I have to say that has significantly increased in the past 60 years. Therefore, in my opinion, any extrapolation regarding durability from these early dams with German plains can only provide a lower boundary of German lens surface like them, and this consideration would give us more confidence even to the damage-free, relatively conservative work. So I'm available for any question during the breaks, and thank you very much for your attention, also on behalf of my
Thank you very much, Mr. Professor Gopi, for the excellent lecture on applications of the geomembranes. So as the time we are running, so the short of the time, so probably you can actually interact with the other for the further clarifications and other information. So now I call up the next speaker, Professor Madhavi Lata. So she is going to talk on micro and macro of sand liquefaction and its mitigation.
You just make sure the profile is there.
Professor Madhavi, you have 16 minutes. Thank you.
Namaskar. Professors K.S. Rao and Mr. Palluri, and the persons behind this show, Dr. Anil, Ashish Juneja and Murthy, and all of you from different parts of the world. Good morning to all of you. In the coming 20 minutes, I am going to put forth some ideas on the micro to macro of sand interactions and their effect on soil diffraction. This work is a summary of 4 PhD theses and 1 MSc thesis at IISc Bangalore. In this slide, I am showing you the collection of sand particles from different parts of the world. It's a very beautiful story of the Earth, where there is continuous upcycling and recycling of sand happening. We have these big mountains which get eroded, particles break, they get transported into rivers, and these sediments consolidate, cemented, and then they are uplifted to again form mountains, and at places where we have divergent boundaries, there is continuous lithosphere formation. The igneous rocks are formed from the magma which is coming up, and these again are upcycled into mountains, they get eroded. This is a continuous story of every sand particle that we see on the Earth's face. And you'll be very surprised to know that each sand particle has its own signature shape and size. In the infinite number of sand particles available in different sand beaches, river banks, no single sand particle is alike. That makes us very curious about how these sand particle shapes and sizes affect our macroscopic phenomena like diffraction. As we all know, the particle size and shape and their effects on the shear strength, particle dynamics, density, packing, fabric, overall compressibility, porosity, permeability, these are all well established in literature. But there is no quantification for the effect of particle shape and size on phenomena like diffraction. For example, we've been adopting this sieve analysis in our designs. We only talk in qualitative terms. We take sieves which have square openings and pass over soils which do not have a different shape. And then we only get a one-dimensional information. And we rely on this shape. And we have no clue of the size and shape of the particles. And all our designs only talk about B10, B60 and effective grain size, which has definitely no relation between macroscopic phenomena. So we are making so much of empirical assumptions here, which I am trying to break through this microscopic work. To put forth some ideas, this is about particle kinematics and how they are affected by the particle shape. Very simple intuitive terms we can understand. If you have rounded particles, their point of contact is one. They can contact at only one point. Whereas if you have irregular particle, you can have multiple contacts. So this changes the way they interact with each other, whether they roll on each other, they interlock with each other, or they are easy to separate, get separated, or it is hard to separate. In a microscopic level, when we understand these interactions, we can definitely understand the macroscopic phenomena like liquefaction, which is manifested during earthquakes. And another important factor that I want to discuss here is the tortuosity. Tortuosity is the length of the path that the fluid takes ways to come from one point and exit through another point. And as the particle shape changes, the length of this path varies, and that actually defines whether the fluid will be easily separating the particles or it needs more pressure to separate the particles. This is something that we need to understand. And to understand this better, we can also just take a E log P curve or EB prime curve, where we have a point A. From there, if you unload or load the particle, if you subject it to undrained loading, the particle's position moves from A to B. Since it's an undrained test, we don't have change in void ratio, and from point A to B it moves, and if you dissipate the water at that point, there is a change in void ratio and it reaches point C. The movement of particle from A to B and B to C is not same for all shapes and sizes. Particularly the shape of the sand particle defines how much time it takes from moving from point A to B or from point B to C. And this is the most important concept of liquefaction, my favorite topic in soil mechanics, which is critical void ratio. Sands have some void ratio where they are very comfortable. We call it equilibrium void ratio. It is not the minimum void ratio, it is not the maximum void ratio, but it is a different void ratio. If you look at it in the deviated stress versus axial strain curve, we can call it as ultimate void ratio. This is the void ratio at which the sand particles get sheared without any volume change. It's a very interesting concept. If you take a loose sand and shear it, at large strain it reaches the same void ratio, and a dense sand will ultimately also reach the same void ratio, which is very, very interesting. The only parameter that controls this critical void ratio is the confining stress. And more importantly, if you look at the void ratio versus effective stress, and this is the critical void ratio line which only depends on effective stress. If we have a soil particle which is falling above the CDR line, we call it loose soil. And if you subject it to undrained condition, it will reach the critical void ratio line by developing positive pore water pressures. If you subject the same soil to drain shearing, it increases it actually reduces its void ratio because it gets compressed and reaches the critical void ratio. Again, the dense sand which falls below the CDR line, if you subject it to undrained loading, it actually develops negative pore water pressure, increasing effective stress and reaches CDR line. And if you subject it to drain shearing, it will expand and reach the CDR line. Any point of time, sand will be trying to reach the CDR line. That's the basic concept. And now we define something called state parameter, which is the difference in the current void ratio on the critical state or steady state void ratio. When your stress, this initial state falls above the steady state line, you have a positive state parameter, which makes it contractive and prone to liquefaction. What falls below is a dense sand which doesn't liquefy easily. And the more the state parameter, the more is the sand's tendency to contract and liquefy. Now with this background, we actually did this kind of densification tests on different binary soils where you have rounded pebbles and then angular gravel particles with fines defined in terms of sand, fine sand, and then we tried to compact them and we plotted the minimum void ratio and maximum void ratio for pebbles and gravels. Very interesting what we see is when you have rounded particles like pebbles, just with 20% fines you will reach a maximum density. Whereas in case of gravels which are subangular, the micro-city analysis, we fill these soils in acrylic tubes and we can precisely quantify the size and shape of the particles. And further, we also use optical profile to understand the roughness. Now, when we do the micro-CD in a 2D slice like this, we do the binarization and further we apply the watershed segmentation to separate the sand particles so that we can quantify the size and shape. In regular watershed segmentation techniques, we either over segment or under segment because of the algorithm issues. So we developed a new algorithm with enhanced high-pass filters which will precisely separate the particles. And now we do the micro analysis. This is the volume visualization of a single particle. We can do multiple particles of a tube full of sand particles at a time. And going forward, this is the multi-level shape characterization. At a macro level, you have sphericity, which represents the closeness of the particle shape to that of the sphere. And at the meso level, you have roundness, which tells us the roundness of your corners. And at micro scale, you have roughness, which tells the microscopic differences in the particle shape. Now, we do this size shape quantification on the scanned particles. We move or rotate the particle so that its principal axis remain the main axis XYZ, and then do the volume equivalent sphere generation. We do the spherical harmonic analysis to understand the convexity, and then precisely regenerate the particle mathematically so that you can get the entire shape parameters from this particle. I am only explaining for a single particle. You do this for hundreds of particles together, and then you generate the microscopic or morphological descriptors known as sphericity, angularity, everything. Now that you have the information, you go for optical profilometry to understand the microscopic parameter, which is roughness. Once you quantify these parameters precisely, put it in a kinematic chart. This chart was developed by my students, Nimisha and Prashant Bangla, where based on the size and shape, you can put the particles in interlocking, semi-interlocking and maximum interlocking zones. Based on this, you understand the kinematics of particles. Now, very interesting aspect of this is when you separate size and shape, particles of same shape, irrespective of their size, exhibit the same critical state line and the same phase transformation. Phase transformation is if you have a loose sand, you subject it to shearing, it develops positive pore water pressure and it mean effective stress reduces and reaches the critical state line. It actually contracts and liquefies. If you have a dense sand, it dilates and it never liquefies. But if you have a medium dense sand, there is a point at which it moves from contractive style to densification style, which we call as phase transformation. Irrespective of the grain size, particles of different shape, right? If your particle shape is different, your critical state line is different. So here we understand that compared to grain size effects, grain shape effects rule the soil liquefaction. To confirm this, we also did the cyclic simple shear test and we understood different processes that lead to liquefaction. For example, progression of pore pressure. Here in one plot I am comparing 5 medium and coarse of different shapes like round, this is semi-round or subangular, this is angular, and across the figures I am comparing different densities. So at every density what we see is coarse sands are more resistant to liquefaction, which is known thing. But what is less known is how between round, subangular and angular particles, here the x-axis scale is different. You should be careful here so that the differences are far more than what you are visualizing here. So a rounded coarse sand liquefies within 25 cycles, whereas angular coarse sand stays up to 150 cycles without getting liquefied. Similar thing when you see this test part, the rounded particles quickly move towards zero shear stress state, whereas the angular particles take more time when they have to reach the zero shear stress state. And when you understand the stress strain response and the hysteresis loop gets widened very quickly for the rounded sand. It takes a large number of cyclic stress cycles to induce liquefaction and angular particles. The cyclic stress stiffness degradation also is very quick for rounded particles, and it actually gets delayed in case of angularity. And then strain energy that is needed to cause liquefaction also very high compared to rounded sand in angular sand particles. So if you see the role of grain size and grain shape, which is summarized here, in essence we know that grain shape is more ruling the liquefaction behavior of sands than grain size, which we have been believing that smaller fine particles liquefy quickly compared to the bigger sand particles. Now you combine the grain size and shape effects to ultimately to give an understanding to the field level liquefaction resistance, which we call cyclic resistance ratio. So if you plot effective grain size and regularity, which is the average of sphericity and roundness, we can plot the cyclic resistance ratio for different sizes and shapes, which tells us that by knowing the grain size and shape parameters, we can understand what is the cyclic resistance ratio. Once we have the cyclic resistance ratio, for any given uptake, the seismic demand is defined in terms of cyclic stress ratio, and the ratio of cyclic resistance ratio to cyclic stress ratio gives you the factor of safety against liquefaction. This is the contribution of grain size and shape to the field level liquefaction, which we verified and confirmed. The reason behind this behavior is very simple. When you have smaller particles, from the cubic packing, which is very loose, to hexagonal packing, which is very dense, to move from this state to this state, you need very minimal change in deformation. You just need to move very little to reach this state. If your grain size is big, you need lot more deformation to move from cubic packing to hexagonal packing. When it comes to grain shape effects, if you have rounded particles, there is a single point of contact. It's easy for the fluid to separate these particles. In case of irregular particles, the fluid will enter between these grains and separate and dismantle all these contacts. It takes far more energy, and that's why these particles are very resistant to liquefaction. Now, about mitigation of liquefaction very quickly, we also try to understand the effect of grain size and shape on the liquefaction mitigation. For example, if you put a single geotextile layer here between the specimen, exactly at the mid-height, and we try to understand the liquefaction response of this specimen with different particle sizes and shapes. And what we understood is, when you put the reinforcement, obviously we used a non-woven geotextile, which is really highly compressible. When you use this non-woven geotextile, apply the cyclic simple shear, there is this interstitial pressures which are developed within the thickness of the geotextile, which will reduce the pore pressure progression. That is why all reinforced specimens are more resistant to liquefaction, but the resistance increases with the grain size and increases more with the grain irregularity. Very heavily dependent on the grain shape, you can see that the rounded particles could only move from 4 cycles to 9 cycles with an inclusion of 1 layer of reinforcement, whereas it moved from 76 cycles to 150 cycles when you have angular particles. So the beneficial effects of reinforcement also are more pronounced in case of irregular particles. And the same thing is shown in terms of role of grain size and shape and the stress path traversed, what I explained, and the widening of hysteresis loops, very quick in case of rounded particles which are reinforced compared to the angular particles with reinforcement. Similarly, cyclic stress degradation is very slow when you have angular particles. And post-liquefaction, strength gain is very quick in case of angular particles compared to rounded particles. To understand the governing mechanism, we also did the interface shear test, and the interface shear strength can be directly correlated to the increase in the liquefaction resistance when you have this layer of geodesy. And this summarizes the overall influence of grain size and shape in case of reinforced sands. You can actually take regularity, angularity, and then other parameters, non-corner aspect ratio, curvature modifications done and tested for a bigger scale, full-scale test as well, where the burning mechanism here is the rounded particles easily roll on the geotextile layer. When you have subangular and angular particles, instead of rolling, they flow through the material, which creates much better adhesion and facial friction, which is the reason for the increase in liquefaction resistance. Now, moving to the bigger scale interpretation, I'm finishing. I only have 2 slides. So this is the shaking table test where we tested bigger level specimens with rounded and angular sands. And then in the shaking table model test, the way the liquefaction occurred is very different for rounded particles and angular particles. In case of rounded particles, you have seen complete flow liquefaction, total zero shear strength within very few cycles. You see cracks orthogonal to the direction of shaking and water coming out in terms of sand voids. Whereas in case of, this is after 20 cycles, this is after 100 cycles. We needed almost 100 cycles to cause limited liquefaction in the specimen, which means that cyclic shear stress, which is above the static shear strength of the sands, is very, very less here. And also the stress reversals are very transient. You only see one crack which is in the direction of the shaking and very limited liquefaction occurring in the sample, vouching for the enhanced liquefaction resistance of the particles which are irregular in shape. Now what is going on in this field in my research is, we are buying a big micro-CP which can scan almost 300 mm by 600 mm specimens, and we can do this before cyclic reaction testing in situ. And then we are also working on 3D printed particles so that we can play around the size and shape and get more clarifications on the flow through the particles of different shapes. And we are also doing the transparent soil experiments to visualize whatever I have explained here theoretically can be seen practically and then complemented with DEM simulations. Thank you so much, and credits go to my students.
Thank you. Excellent. I think we will have the discussions about during the tea time. So I will call upon the next speaker, Professor Jan. So he is also again going to speak on the liquefaction aspects.
Thank you, Mr. Chairman. The topic of my unified model is application to the reliquefaction. My main focus is on the constitutive and briefly introduce its applications. Two parts of my talk. The unified description of a soft soil. So, sometimes we always consider what is the most influential factor on the mechanical behavior of soil. And the three are the most important. One is over consolidation, or sometimes we call it as density. The second is the structure, where the soil is disturbed, undisturbed, naturally deposited soil. And the third one is the anisotropy. Here, we mainly consider stress-induced anisotropy. The other condition that influence the soil behavior is also dependent on the external condition, which we call the drain or undrained. For soil, undrained or drained is totally different. The monotonic or cyclic loadings is sometimes always contribute, and the people used to divide these two different loads for different description. And of course, there are other loading paths apart from conventional dry conditions, so true tricycle conditions, or the coaxial, non-coaxial behavior plasticity, etc. But mainly we focus on three major influences. So, if we consider here, I just focus on the sand. For loose sand, or medium dense sand, or dense sand, the soil behavior is quite different. And also for undrained or drained behavior is also different. The purpose of the research is to describe the sand under different loadings and under different, the densities, the naturally deposited soil or undisturbed soil, and also the experience stress history, or what we can say, the stress-induced anisotropy. So why we should do that? A very simple question is, why loose sand would liquefy? But for dense sand, it doesn't liquefy. And also, we observed a very interesting behavior that during 2011 Great East Japan earthquakes, we find the main shock, the sand didn't liquefy, but the aftershock, much less than liquefy. Why such kind of peculiar behavior happened? So for here we prepare a set of sand with different density. The interesting thing is invented by Professor Asao of Nagoya University. And with isotropic consolidation, and vibration loadings, we start from the same losses set densities, and with different loading part, we can get a set of sand with different densities. And then we apply the load with undrained conditions and drained conditions. Here I should emphasize, this is not experiment result, but the numeric result that, calculated by the constituent. I propose we call it as unified model for sand. It is quite easy for you to understand. For undrained conditions, loose sands, flow liquefaction, static flow liquefaction, phase transition. For dense sand, it looks just like almost linear increase. Very dense sand, this is effective stress cost, and this is the stress strain relations, and also in the E log P for undrained conditions, they all moved to aftershave, moved to critical state. And for drained conditions, loose sand show strong strain softening and shear dilators, but for loose sand, it just show negative dilators. Move gradually from soft loose sand, dense sand. And also you can find, if we look at these sands start at a different point, but finally at the critical state, they all move to the same point. That means the sand is the same way, but at the different conditions. However, when you shear them to the critical state, they will to the same destination. That means the sand under undrained and drained condition, they describe unique. Then you look at this is a very famous result. This is also a numerical calculation by constituting model. You can see for loose sand, this is number one. Loose sand is flow liquefaction, but for medium dense sand, there is cyclic mobilities, the regaining of the stiffness under the cyclic undrained loading. But for dense sand, you can see it will never liquefy and looks like clay soil. So this behavior also shows the liquefaction is loose sand, medium dense, and dense sand. but I should emphasize this constitutive model only uses 8 parameters, among which 5 are totally the same as vertical state soil, Canton models. And the other 3 parameters just control the 3 key issues, that the evolution of density, the evolution of a structure, that means decomposed of natural structures, and another, the stress-induced anisotropy. So you can find, in this way, the sand with different density, subject to different loads under different conditions, they are all using one set of parameters without changing any value of materials. And here I should introduce a very interesting test result. The test result was conducted by Hinokio, the PhD candidate of Nagoya Institute of Technology, where I worked for 25 years as a professor. And the test is quite simple, using true tricycle test, and give assigned loadings. You can see this is sigma 1 by sigma 3. The shear stress ratios at the critical state is 4.7, with not dynamic, just cycling loading to the 4, +4 to -4. And you can see the shear dynamics at the beginning, because this is a very dense sand. You can see at the beginning, just contracted, shear contracted, and then transformed to strong shear dynamics. And then you go back, because it's cyclic loading, and you can see this is a typical glass. You can see, but the volumetric strain during the shearing is graduated compression. However, it will finally, turn to a stable point without any further change of volumetric strains. And this is the numerical simulation with constitutive model. I never say cross-discipline is a theory. It's just a numerical calculation. And you can see this is the calculation result. And finally, it turned to the limitations that will never go first. However, if you don't use the constitutive model I proposed here, or the model, if you continue change, it will go on without limitations, with very, very large, unlimited volumetric shearing. So it is quite interesting. And you can see this is the shear stress strain ratios, and after 7 or around the 10, you can see around the 10 circles, it will stable, what we call as a finally reached to near elastic conditions. However, you can see this is the calculated result. Also, finally reached to a stable condition without any change. And this is another, because I don't have enough time, what I should emphasize is that there are many constitutive models describe the density effect, the structure effect, and the stress-induced anisotropy effect. However, these 3 factors are not independent in the way that we find these 3 influential factors are influence each other, and we find this intimate relation and give a numerical model. Now also, this is a very famous test result, what we call as the confining stress tendency. The test result was conducted by Professor Ishihara and his student. It's a very amazing, Professor Ishihara gave his ranking lecture at 1993. That means for loose cell, under different conditions, the behaviors like a dense cell, if confined stress is very small, just like this one. Because I don't have enough time to describe this behavior, you can, this one is the test result. It's amazing because in the way you can see, under 2 megapascal and very loose cell, you can, the test can keep the same. It is almost incredible. I discussed with Professor Ishihara and asked him, how can you do such kind of test? And I guess this test is by frozen method, and he told me it's true. And this is the calculation result. This is the calculation result. Also, the similar tendency with Tesla. Be careful about it. All the calculations are used the same parameter. You can find all the paper I published related to Toyographen. All the parameter is the same. That means Toyographen only has one set of parameters with this constituting model. So also, Dr. Yamada also did a very nice test result. What we can say is anisotrope. First, if a liquefaction, after a severe liquefaction and consolidated to isotropic consolidated to initial state, and then shear with different direction. And this is the test result. You can see the totally different from compression to dilation. You can see for this one, A, for this one, you can see. They're totally different. And then this is the test result. The test result of this is the numerical calculation and the test result. Why I should here give the compression? Because this phenomenon is not so familiar with the people. So I emphasize this one. The constitutive model can roughly describe the stress in this anisotropic quantity. So I don't have enough time to describe the constitutive model. We use the subloading concept and superloading concept, and maybe subloading people know it is physically the same as bonding surface. And this is our constitutive model, also using the same concept, but very clearly with only 8 parameters, and the yielding surface with 3 new evolution equations, and finally, because this is finite deformation schemes, I just passed away. And then, 5 minutes, 2 minutes, okay. I just show you a very interesting behavior. This is my because I think I have enough time. I just using some Japanese words because, for instance, in the main shop, the liquefaction area is very limited. However, in the second shop, after shop, all area liquefied, very serious. And then you can see, this is, I don't have enough time. There's 3D. I just show you a very interesting pass. So, this is very interesting because the calculation was conducted in May 26. The result, we don't know the detail of the liquefaction because all these data are open in the network, in the website. All people can get the soil profiles, the material based on the design method to fix the 8 parameters, and also we have the observation of the equal earthquake waves in the 3 dimensions. And then we just consider, because we should explain why the first shock, main shock, the soil don't liquefy, and in the second shock it liquefies. You can see we just conducted 3 patterns because the liquefaction and consolidation are conducted in the uniform ways, because we don't need to describe the load is monotonic loading or the cyclic loading. It's just depend on the vibration, the dynamic force, and the viscosity force should be considered or not. All calculations are in the time signature without any intervening of human being. And then we consider the main shock. 2 cases. 1 case is the main shock and 2 cases, and consider 50 years consolidation, because after the main shock stopped, it will soon go to process of consolidation. And then we calculated another case with only, aftershock without main shock, and then you can see. I will give you one time. And this is the test result, because all the calculations, we never change the parameters, static or dynamic. Just ask him, the him is the machine, to calculate. Put in one set of parameters and just calculate with the time signature of earthquakes. And you can see this one, the major shock, 80 guard. The aftershock 25 bars. The earthquake is not enough to make soil liquid. However, you can see in this case, the main shock, you can see. The first liquefaction, this is the case. The first main shock and aftershock all liquefied. You can see that this is the excess pore water pressure ratio. 1.0 means totally liquefied. And after 5 minutes vibrations, it stopped, but the excess pore water pressure, dissipated very slowly. And after 24 minutes, the aftershock comes. And it liquefied again. However, you can see, I showed you, I will soon finish. You can see, in the aftershock, the liquefaction, the excess pore water pressure ratio is around 0.7. However, with the second aftershock, it soon come into what that means liquefied. However, if without the main shock, this means the excess pore water pressure only increased 0.5. It is almost 6 times if you have the experience of main shock. So the aftershock, why $25 earthquake can make the soil liquefaction again? 2 reasons. One reason is that the liquefied soil didn't dissipate completely or the consolidate completely. There are 70% excess pore water pressure remains. The second one is that after liquefaction, the soil experiences strong induced anisotropy. So I just make an explanation like the boxing. If 2 boxers, they have the same powers, they box, they fight each other at the first 3 rounds, even if they hit the counterpart, it will not be KO. However, if after 10 or 11 rounds of fight, every people get very wounded, severe wounded, then if you give another punch, you can kick off and KO you very quickly. So this is why 25 guards aftershock can make soil liquefy again.
Professor Jani,
Sorry.
Yes,
Thank you. Sorry. Thank you very much.
Excellent lecture, by Professor Jani, we are very sorry, that not to allow any questions. I think we will be taking up, that during the lunch time or maybe, the tea time immediately. So we completed, 3 keynote, so they invited lectures. And now I call upon, the keynote, so that is getting sorted, Professor. So please, you have 30 minutes, sir.
Thank you.
Thank you.
First of all, thank you very much for having me over here. It's great to be in Goa. Start my presentation. All right. So the title of my presentation is Smart Geotechnical Infrastructure: The Value of Distributed Sensing for Geotechnical Engineering. Just to start by saying that in geotechnical engineering we have a lot of exciting things going on. This particular graph shows that vertical axis is expectation, horizontal axis time, and you can see the evolution of any technology. Initially it has a height, it has a height that goes up, and then it goes down, and then you bring it to the market. You can see that some of the technology like LiDAR, wireless sensor network, digital image have gone to the market now. It took about 10 years to go from here to here. Obviously, the excitement right now is AI and machine learning. And then there are other technology that you may be working on your research to bring it to the reality. What I want to do today is a little bit focus on distributed fiber optic sensing because it took me about 10 years, 20 years to bring it to this particular location. But hopefully you'll find it interesting. Just to start by saying that there are a lot of interesting technologies that can measure movement nowadays, and I'm sure you're using these technologies for your practice. The most important one is computer vision, LiDAR, and UAVs. What you can do is that you can measure in the order of 0.1 millimeter and 1 millimeter, which is the area range that you really want to measure in geotechnical engineering practice. Satellite is coming. Satellite will have about 10 to 20 millimeter precision. And what I want to do today is to give you a little bit more information about distributed fiber optic sensing. Obviously, as a geotechnical engineer, civil engineer, we tend to design our infrastructure for 100 years, or maybe 75 years, or 120 years. We want to extend the life because many of our infrastructure does exist more than 150 years, but you may have some disruptive events. If you look at many sort of urban cities like Goa, probably Goa 20 years ago, totally different. Now it's like this, but maybe 20 years it's going to be different. In other words, when we say aging infrastructure, it's not about material aging. We're changing and we're making sort of additional loads to our infrastructure, and therefore it changes all the time. So can we make our infrastructure more adaptive compared to rigid design is something that we need to think about. In order to do that, you really need to have some sensors. We want to learn what's going on. So let's imagine a world where future generations no longer have to worry about aging infrastructure. So I'm going to give you 3 examples that we've been working in this particular situation. So these are the water main pipes that you may see sometimes in your city. This is how you fix it. That's a lot of work. It would be nice to have a robot to do this, but at the moment we don't have a robot to do this. But that would be something that we can look at the future. This is where I live. This is Berkeley over here. San Francisco is on your left. And we have a fault zone called Hayward Fault. And these dots are about, it is the ground-related movement that caused the water main breaks. So in 30 years, we have many of the breaks. And it's very close to, because due to landslide and fault movements. One technology I want to introduce you today is distributed fiber optic sensing. It's a standard optical fiber that you use for telecommunication. That means that when you send a digital signal from one side to the other, you can see the light coming out from the other side, and you have a sort of a data that comes with the light. However, sunlight, if you shoot a light, sunlight comes back to this particular box. And we know where it came back from because you time it, you shoot a light, and the light coming back early is close to you. And then coming back later on is further away from you. However, what you can do, a light coming from a particular location, I can find out what is the temperature, what is the strain, what are the vibration at this particular location, or tens of kilometers. So let's use this technology. So this is again Hayward Fault. This is our campus. This is a site that we did an installation of this fiber optic sensor. Just to give you a little bit of context, every road has pipelines. So these are all the water main pipelines, water pipes, distribution lines. You see different colors. The reason why is that in Berkeley, this is close to the bay, and then you go up to the hill, and there's a hill on the top, and you go to the other side of the hill. And our Berkeley campus is elevation of 109 meters. The other side of the hill, where we have a water treatment plant, is 107 meters. So every day we bring the water to over here, but in order to raise the pressure, every day we pump the water up to these two tanks to keep the pressure high. So when you open a tap, you get your water. Unfortunately, as you'll see over here, Hayward Fault crosses these pipelines that will provide water to our pink zone. So what we did is that when they replaced their pipeline 2 years ago, it's a plastic pipe. The diameter of the pipe is 0.91 meter, and then there's another one 0.55 meter. And you can see that this is the roadway where the pipelines were replaced. And then we attached a fiber optics line on top of the pipe as well as in the trench. And these are the fiber optic cables attached or buried in the ground. Now this is the Hayward Fault. This side, your left side moves up, your right side down. Actually this fault is creeping, so every year it moves about 4 millimeter every year. So there's a 4 millimeter movement which allows this particular pipe to stretch and bend as it goes. So this is the video of the trench where you have that plastic pipe, and on top you see these 3 lines where we attach the optical fiber, and then you have a tape, but then with epoxy glue all the way along to fix the cable to the pipe. Now you start taking measurement, and in the summer, pipe expands a little bit because of the thermal expansion of the pipe, plastic, and then during the winter it compresses, it shrinks due to the thermal contraction. However, with time you start to see more strength concentration around the flow across the zone. The strain is about 100 microstrain. It's very, very small, but you can see it. And then you can see the mechanism. If you have 3 cables, you can start to see a tension, which is stretching because this side and the other side is moving relative to each other. Tension, and then a little bit more bending happening at the curvature points. You can integrate the strain, and then looking at how much extension the cable is having. So if you integrate from one end, and the other side is 200 meters, you can see that during the splinter, sort of like it shrinks for about 0.005 meters, that means about 5 millimeters. But then with time during the summer, it goes up to expand, but then around the fault zone, you see more concentrated strain and displacement developing. And so now we're coming to the summer, and then it's rising up, but you do see a more displacement along the fault zone. So now you can see it. The also important thing is that you always have to do the error estimate. And you can do the error estimate through the mathematics. And what you see is that it's not a full line, there's a sort of a boundary line shown over here, and the error is very, very small in that sense that this is an actual movement. So in other words, you can measure the movement in the millimeter scale across the 200 meter pipeline. This one is after 18 months, it shifted for about 4 millimeters. And then we do have a satellite monitoring data. So this is a satellite monitoring data. One side on the red zone is moving up. One side, the other side on the blue zone is moving down. And if you look at the difference in the movement, it's about 4 millimeters. So in other words, that satellite for many tens of years of data matches with the data that I showed you using fiber optics. So fascinating, isn't it? So we're start to do, okay, rather than having a point strain, let's try to measure distributed strain to assess our infrastructure. So we have a project with California Energy Commission to look at different types of technology, and tomorrow, or maybe the day after tomorrow, my colleague, Professor Dimitrios Zekos, will probably show more about UAVs. We work together to look at pipeline distribution strain, and then using that distributed strain, we understand the mechanism, and based on that, we update the parameters to a better prediction. Here's another site where we attach the fiber optics on the gas pipelines over here. So the point here is that once a pipe is buried, we're not going to see it for that another 100 years. Meaning that you see the pipe over here, but probably you're not going to see it again, because I'll be dead already by then. So the point here is that why not embed intelligence during construction for future generations? Fiber optics can be fun. So you can attach the fiber optics on a pavement like this, and then you can have your dog running, and you can see your dog running. And so we're making this particular road like a touch screen. And the project is with car manufacturing company to make, how can we make the road safe with dogs and people where there's an autonomous car talking to each other. Every road has a fiber optics already for your telecommunication because of the fiber optic communication. We have a site, we borrow one of the line that's already in the ground, which is from here, which is the city of Richmond, to the Berkeley, to Oakland. So this length is about 25 kilometers of fiber that is already embedded because of the communication, but we're using that to detect anything happening along that road. And what you see over here these all lines correspond to a car moving on that particular road. So this particular road car is moving over here in the direction of this particular direction with time, and actually the braking is the speed of the car, and you can see the activity going on this particular road. So we're trying to check whether we can measure water leaks or car movement or looking at the traffic or pavement degradation with this particular technology. You can also use fiber optic to listen. So this is a project where we have a floating wind turbine, and then there are some moor lines where we put the fiber optics to measure distress strain. But we can also listen to whales singing as well. So if you hear this in the background, we hear the whales singing, and this is recorded by fiber optics. Okay, so a little bit more back to geotechnical engineering. This is a project with Caltrans, California Transportation Department. This is a pile. So we have 4 different piles. Actually, it's called post-graded shafts, where you inject ground at the bottom to increase the bottom stiffness. And then this is the sort of a profile called penetration test results to look at the soil profile. But we have 4 different tests, vertically loaded piles, and we attach the fiber to these 4 piles. The piles were over here, so you can see the pile loading. We attach the fiber at 4 different locations to measure strain at 4 different locations of the pile in the vertically loaded condition. This is the load displacement profile that you know very well, load versus displacement at the top. What we do is that as you apply the load from the top, you measure how much strain is developing as you apply the load. Obviously, a larger strain will develop at the top and decreases due to shaft friction. Okay, so let's look at the data. So we have 4 different lines, but I'll go back again. We also have vibrating wire strainage at different locations, which may be a typical thing that you do. So this is the first data set. I apply the load, and then vertical axis, the distance from the top, and then horizontal is a strain. And you can see that the vibrating wire strainage shows you larger strain at the top and decreases to some value with the load coming to the bottom of the shaft. I just want you to look at this particular data set. So when you have this data set, what would you do? You say, oh, well, that's not a good data, I'm going to throw this away. But let's look at the actual fiber optics data. Actual fiber optic data looks like this. You can see that it matches with the actual vibrating wire strain gauge. If you don't have the fiber optics, you may say, what's going on this one? But the point here is that purple line is this particular point. Red one is the opposite. In other words, pile is bending as you apply your vertical load because of the anomalies in how you apply your load. And then you can see one direction is sort of a bending and the other direction. But also you can see that it's bending in one direction as you go, but then if you go to the bottom, it flips and bends to the other direction. So again, the actually vertically loaded pile may not just vertically load, but also can bend depending on how you do the test. If I take the average of the data, which you see at the end of the bar, you can see a very nice shaft friction developing as a strain decreases with depth. So in average, it looks good, but actual behavior is bending. So the question is that, what is the effect of this bending? I have to load it vertically, sometimes because the piles are not homogeneous, it bends a little bit and you see anomalous behavior. So that's the real performance. If you know you have force strain, then what you can do is integrate twice to get the shape of the pile, how it's bending as you apply your load. And this is called, we call shape sensing from distributed fiber optic sensing. So horizontal, vertical axis is depth. And this is the movement in X, Y direction as you go deep. And you can see different form piles bends a little bit in the order of few millimeters that we can measure. But it bends a little bit even you apply your vertical load. And then you can see which way it's bending depending on how the testing is done. So again, you can start to see, even though you try your best to vertically load, sometimes anomaly creates a little bit interesting behavior. And that's part of the uncertainty. Actually, when you look at the data and record very carefully, the pile is not vertically loaded and there was some eccentricity in the loading application. So in other words, even though you have a pile head, your pile tip, because the pile is not always vertically down, as you excavate, it can go a little bit tilted, and therefore you have an eccentricity even you try to make a vertical pile. So one thing we can do is that you can do some simulation where you can have your pile with the load from the top, shaft friction, and then you have a tip resistance. That will be what you will do with the vertically loaded pile. But also, as you can apply a lateral resistance because it's bending a little bit. So I can put the eccentricity and then try to get this. But our ultimate aim is to find out what is the TZ relationship, what is the friction, shaft friction with displacement at different parts of the pile. So you can do a simple FE analysis to back calculate what are the TZ relationships along the pile. So the top figure, so the figure on the left top shows you a TZ relationship where you have a shaft friction with displacement, and then we have this TZ relationship. What you want to look at is a solid line is the condition of eccentrically loaded, and then you back calculate what your TZ is going to be by the back analysis is the solid line. The dotted line is if you assume there's no eccentricity and trying to back calculate what we do in practice. In this particular case, if you see, and then you're looking at different depths, because every depth you have a different friction because the confining pressure and the solid property changes. What you can see at some location, you see that the eccentric loaded and non-eccentric loading gives you back calculate same TZ relationship. In other words, the eccentricity didn't really matter. And in general, the variation is small. So the conclusion is that even though the pile were eccentrically loaded, the back calculated TZ curve doesn't matter much in this particular case. Now what you can do next is that, remember we had a vibrating wire strain gauge, which is only discrete, 6 of them, and then you do back calculate the TZ relationship, and that's what you get over here. So these are the back calculated TZ relationship from the vibrating wire strain gauge, but we also calculate the uncertainty in the data set. So the shadow zone is the uncertainty. So here we have a small uncertainty because we have lots of data along the pile. Whereas if you have vibrating wire strain gauge, you have large uncertainty because you only have few data sets. So what you can do see on the right figure is the large uncertainty if you only have few data sets. But if you start to have lots of data like distributed fiber optic sensing, you see the blue line with small amount of shadow, you be more confident about your TC relationship. Here's the final case I want to show you in London, where we had a big pile driven down for about 80 meters, with the diameter of the pile was about 2 meters or so. Again, we attached the fiber optics, so optical fiber is attached at 4 different locations, but also we have a temperature cable that measures the temperature all the way along the fiber down to the bottom of the pile. And what you do is that you attach the optical fiber in your cage and you fill the concrete, but what you do is that you attach the cable and you splice it, so if you shoot a light, you get temperature data and strain data in one measurement. And you take that reading every time you want to take your reading. When you attach a cable, what you do is that as you bring down your cage like this, you have your cable roll through together with your cage, and then you attach it. The most important thing is that you want to make sure that your contractor or the construction crew is happy with what they do. You don't want to delay any construction, so you start to figure out what is the best way to attach the cables. So therefore, there's no disturbance from the construction point of view. 5 minutes. Yeah, I see 5 minutes. Okay, thank you. Okay, I'll finish. So what you can do is that you can measure your temperature change during the curing of the concrete. Meaning that we measure our temperature as we go along. You measure the temperature during the concrete curing, which allows us to measure how the concrete is curing with time after the installation of your pipe. And from this, what we can do is that you can see at every point along the pile, I see how temperature rises and decreases due to the hydration. And then you can do what we call a FE analysis of how the temperature dissipates, that heat dissipates into the ground. And the uncertainty is what is the size of the radius of the pile, because if your pile is large radius, it dissipates in a different way. If you have a short radius, it dissipates in a different way. And you can calibrate to create a shape of the pile. So this is called thermal integrity testing. And this is the pile shape derived by the temperature data that we have. What I want to show you is actually the dimension. I showed you earlier, you see the pile going up and down and increasing and decreasing with radius. But this is the shape. It's not really random and also transition. But I want to show that it's a smooth transition from larger radius to smaller radius. And that's the shape of the pile. After that, what you can do is that you can apply a load. So this is a whole cell that you can apply a load, so you can see the load distribution and how strain changes as you apply the load. And this is the strain data. You see the strain data over here with the fiber optics. And you can see a zigzag of the data. You may not like it, but I'll come back to this later on. You may not like it, but it may be similar to the strain gauge. I have 4 cables in this particular pile. If I plot the first cable, it looks like this. If I plot the second cable, it looks like this. If I plot the third cable, it looks like this. And then if the fourth cable, it looks like this. Every strain location, exact zone location, show an increase or decrease in a very uniform way. In other words, this up and down is not due to the instrumentation issue. It's about the real performance of the pile or the anomalies that you have in your pile. And you can see up and down exactly the same location. And then you can derive your TZ relation So this is the shaft revisited and displacement. So the point here is that if you put your fiber optics in your pile, you can look at quality control, you can look at real-world performance, you can look at future-proofing, and perhaps you can use it when you want to reuse your pile. I just want to finish off this particular slide by showing that, remember I showed you the up and downs in your pile rate from the thermal measurements. So this is the thermally derived radius, and you see up and downs. And then this is the strain data. When you mechanically load, you see up and down. And the point is that when you see down, it goes up. In other words, if your radius decreases, your stiffness decreases, so your strain increases. And in other words, you see independent measurements of the radius by the temperature data corresponds nicely to the mechanical performance of your pile. And in other words, what you're trying to see in up and down radius is reflected in your strain. So in summary, what I wanted to show you today is that there are a lot of opportunities in geotechnical engineering using this particular technology. Why don't we start using it for quality control, maintenance, resilience against hazards, reuse in particular, and then trying to look at what we call new generation of observational method. And then I want to finish off by saying that I went too fast today, so I'm very sorry about it. If you want to know more about it, please go to this YouTube, which talks about more about it in my right lecture. And also, if you want to know what we do, I think Professor Zekos will talk about some other things that we do at UC Berkeley under the Berkeley Center for Smart Infrastructure. And then when you have time, please visit UC Berkeley. Thank you very much.
Thank you, Professor Ganesh, for the excellent lecture. I think we have three invited lectures, and then it was one keynote. The whole session has went up very well without the question and answers in the session. So we'll take up the questions and respective answers from the presenters, so maybe during the time. Thank you very much. I'm handing over also the mic to the organizers.
Thank you, sir. I now request the chair of this session, Professor K.S. Rao, to present the memento to Professor Kenichi Soga. I request the co-chair also to join. Professor Kesufi Daniel Antonio onto the dais. Request Professor K.S. Rao to hand over a memento to Professor Kesufi as a token of our gratitude. I request Professor G. Madhavi Gada to be on stage. Request the chair and co-chair of the session to hand over a memento to Professor Madhavi Gada as a token of our appreciation. I request Professor Feng Zhang to be on stage.
Where I
Thank you. I request Professor Ayodhya Raman, the Vice Chairperson of Geotech Asia 2025, to come forward to present the mementos to Professor K.S. Rao, the Chair of the session, well as to the engineer Sridhar Valluri, the co-chair of this session. Thank you all. Ladies and gentlemen, there's an important announcement awaiting you all. I invite Dr. Anil Joseph, Professor Ashish Juneja, and Professor Dasaka Murthy, the organizing chairpersons of Geotech Asia 2025, onto the stage. On behalf of Dr. Helmut F. Schweger, President of the Austrian Geotechnical Society and the Chair of ICSMGE 2026, they will make the announcement.
Good morning, all. So, the Helmut is not able to make it to here. He has asked us to share the presentation, the organizing chairpersons to share the presentation. On their behalf, inviting all to Vienna. Let's see the slides. So these are the dates, 14 to 19 June 2026. And there are 1,424 papers. Review process is going on by each national societies. The assigned operation confirmed, 8 easy honors lectures confirmed, 3 state-of-the-art lectures confirmed, 3 invited lectures, on-market session confirmed, and these are the theses there. We have a small video. Please play.
Welcome to Vienna for the 21st International Conference on Soil Mechanics and Geotechnical Engineering. Welcome to a conference on geotechnical challenges in a changing environment.
This is where it all began. At TU Wien, in Vienna, where Karl Terzaghi and his colleague Arthur Casagrande established the first institute and laboratory for soil mechanics at the end of the 1920s, which can be regarded as the origin of modern soil mechanics. On the occasion of the 21st ICSMGE, some of the original equipment Terzaghi developed for his research will be exhibited in a small museum that can be visited by delegates.
The conference covers all aspects of geotechnical engineering, including a wide range of problems related to the consequences of climate change. For the first time in this conference series, an entire plenary session will be dedicated to specialist contractors, in which they will present their efforts to reduce CO2 emissions in geotechnical engineering and highlight their achievements and further developments on the way to sustainable geotechnical structures.
My name is Tuve, and I work for a worldwide operating special contractor. The conference in Vienna will be the perfect opportunity for young geotechnical engineers to explore a career opportunity in geotechnical engineering with authorities, contractors, and designers. Enjoy!
To underline the importance of the industry in the construction of public transport infrastructure and the transition to renewable energy generation, all global players in geotechnical engineering are expected to be represented at the conference, which will provide ample space for exhibitions. Vienna is located in the heart of Europe and is easy to reach by public transport, with overnight train connections from many European cities, making it possible to travel to this green event conference in an environmentally friendly way. Vienna is always worth a visit with its wide range of historical and modern tourist attractions.
As president of the Austrian Geotechnical Society, I invite you to join us in Vienna in June 2026 for a memorable 21st conference on soil mechanics and geotechnical engineering.
Thank you. I now request Dr. Mark Bellows, the president of ISSMG, to join the chairpersons on stage.
Since I'm here, I have to stress on a few things. This conference, and I didn't mention, commemorates 100 years of modern geotechnics. And it's very important for all of us to be there. And another thing, you have to go there and say goodbye to me as president. And we will have a session on the Heritage Time Capsule this conference, which will explain what's going to happen in Vienna, where we will have a physical time capsule sealed for the next 100 years. And it's going to be a very important event within a very important conference. As you see, the contractors will have a say, the researchers will have a say, and I expect all of you to be there, telling you goodbye there. Thank you very much for the organizers for showing this video, and to Helmut who couldn't make it. We'll tell him it's well done.
Thank you, sir. Ladies and gentlemen, that was about the 21st International Conference on Soil Mechanics and Geotechnical Engineering to be held in Vienna in June 2026. We are going to start off with our plenary session 4 sharp at 11 a.m. The tea and coffee is arranged outside. We don't have a time for actually a break. We will be starting sharp at 11 with plenary session 4 with 3 keynote lectures, 3 announcements of which 2 are upcoming conferences and 4 corporate presentations. Please help us maintain the tape, requesting all of you to be back here by 11 a.m. Thank you all.
ರೆಕಾರ್ಡ್ ಆಫ್ ಮಾಡೋದಕ್ಕೆ ನೋಡೋದು ಬೇಡ ಆಫ್ ಮಾಡೋಣ 5 ನಿಮಿಷ ಆಯಿತು.